Welcome to the Coco YouTube channel. Subscribe to our channel to watch new videos like this. Ocker calls the new sign a plasma wave outflow, and it, as well, seemed to follow the thickness of interstellar space. At the point when the sudden whistles showed up in the information, the tone of the outflow rises and falls with them. The sign likewise looks like one saw in Earth's upper environment that is known to follow the electron thickness there. This is truly energizing, since we can consistently test the thickness over an extremely extended length of room, the longest stretch of room that we have up until now, said Ocker. This gives us the most complete guide of the thickness and the interstellar medium as seen by Voyager. In view of the sign, electron thickness around Voyager 1 began ascending in 2013 and arrived at its present levels about mid-2015, an approximately 40 overlay expansion in thickness. The rocket seems, by all accounts, to be in a comparable thickness range, for certain changes, through the whole dataset they dissected, which finished in mid-2020. Ocker and her associates are presently attempting to foster an actual model of how the plasma wave discharge is created that will be vital to deciphering it. Meanwhile, Voyager 1's plasma wave subsystem continues to send back information farther and farther from home, where each new disclosure can possibly make us reconsider our home in the universe. Up to this point, each rocket in history had made the entirety of its estimations inside our heliosphere, the attractive air pocket expanded by our Sun. Yet, on August 25, 2012, NASA's Voyager 1 changed that. As it crossed the heliosphere's limit, it turned into the main human-made item to enter and measure interstellar space. Presently 8 years into its interstellar excursion, Voyager 1's information is yielding new experiences into what that wilderness resembles. On the off chance that our heliosphere is a boat cruising interstellar waters, Voyager 1 is a day-to-day existence pontoon just dropped from the deck, resolved to review the flows. For the present, any difficult situations it feels are generally from our heliosphere's wake. Be that as it may, further away, it will detect the stirrings from sources further in the universe. In the end, our heliosphere's quality will blur from its estimations totally. We have a few thoughts regarding how far Voyager will begin seeing more unadulterated interstellar waters, in a manner of speaking, said Stella Ocker, a Ph.D. understudy at Cornell University in Ithaca, New York, and the most up-to-date individual from the Voyager group. Yet, we're not completely sure when we'll arrive at that point. Ocker's new investigation, distributed on Monday in Nature Astronomy, reports what might be the principal persistent estimation of the thickness of material in interstellar space. This discovery offers us another approach to quantify the thickness of interstellar space and opens up another pathway for us to investigate the design of the exceptionally close-by interstellar medium, Ocker said. At the point when one pictures the stuff between the stars, space experts consider it the interstellar medium, a spread-out soup of particles and radiation, one may envision a quiet, peaceful climate. That would be an error. I have utilized the expression the quiet interstellar medium, yet you can discover heaps of spots that are not especially tranquil, said Jim Cordes, space physicist at Cornell and co-creator of the paper. Like the sea, the interstellar medium is brimming with violent waves. The biggest come from our cosmic system's turn, as space spreads against itself and presents undulations many light years across. More modest waves surge from cosmic explosion impacts, extending billions of miles from one peak to another. The littlest waves are typically from our own sun, as sun-based ejections send shock waves through space that penetrate our heliosphere's coating. These slamming waves uncover hints about the thickness of the interstellar medium, a worth that influences our comprehension of the state of our heliosphere, how stars structure, and surprisingly our own area in the system. As these waves resonate through space, they vibrate the electrons around them, which ring out at trademark frequencies relying upon how packed together they are. The higher the pitch of that ringing, the higher the electron thickness. Explorer 1 S plasma wave subsystem, which incorporates two rabbit-ear receiving wires standing out 30 feet behind the shuttle, was intended to hear that ringing. In November 2012, 90 days in the wake of leaving the heliosphere, Voyager 1 heard interstellar sounds. Interestingly, a half-year after the fact, another whistle showed up, this time stronger and surprisingly more shrill. The interstellar medium gave off an impression of being getting thicker, and rapidly. These transitory whistles proceed at unpredictable stretches in Voyager's information today. They're a superb method to consider the interstellar medium's thickness, however it takes some persistence. They've just been seen about once per year, so depending on these sort of random occasions implied that our guide of the thickness of interstellar space was somewhat inadequate, Ocker said. Ocker set off to track down a running proportion of interstellar medium thickness to fill in the holes, one that doesn't rely upon a periodic shockwaves proliferating out from the sun. Subsequent to sifting through Voyager 1 S information, searching for feeble yet reliable signs, she tracked down a promising up-and-comer. It began to get in mid-2017, close to the hour of another whistle. "It's anything but a solitary tone," said Ocker. Also, over the long run, we do see it change, yet the manner in which the recurrence moves around reveals to us how the thickness is evolving. Thank you so much for joining our video. Subscribe to our channel to watch new videos like this. Don't forget to share the video with your friends.